Okay, great. And yeah, and I really appreciate the efforts of Dave McCallum and the rest of the organizing committee to put together this incredible program and for inviting me here to present as well. So I'm going to be talking a little more broadly about propagating uncertainties within looking at taking things from the ground motions through to the performance of buildings and infrastructure. The work I'm presenting is really work that's going on in this Near East Sim Center, an NSF funded effort really to develop computational tools. And in particular, we're focusing on kind of workflows to kind of propagate information along with the uncertainties through from the ground motions, the responsive structures, and into finally performance. And I'm starting with this slide here that many of you, if you followed PEER for years, the so-called PEER performance-based framework. It's interesting what Norm just described. Down at this IM parameter, there's a whole world of geoscience, geophysics, and there's all the uncertainties there. Each module of this going up to the responsive structures, looking at damage, and finally translating that to decision variables, that one can peel apart each one of those, and that there's similarly challenging problems and kind of characterize the behavior and the uncertainties. So a key part of the PEER framework, kind of behind those, kind of what are the metrics to carry over from one part of the problem to the other. And it's a very multidisciplinary one, going from earth scientists to engineering and at the end to economics and other social science, kind of characterizing the parameters very carefully. And one of the things we're working in the Sim Center is trying to kind of package analysis models and keep track of data to put together kind of seamless workflows where one can do this performance-based assessment, not just for one building, but for looking this over large regions. So the Sim Center computational workflows, you could think of these kind of puzzle pieces. And Frank McKenna, I think, who's on the line now, is kind of the chief software architect here that kind of put together this idea. But the idea is, if you look at these puzzle pieces, starting at the left side, if you think of a regional simulation describing the assets, the inventory of buildings and features, also the hazard, things we've been talking a lot for the last day and a half, simulating response, and all the way over to assessing damage, but also starting to look at recovery. When we think of resilience, that's kind of the key metric. So the idea of these workflows is to encapsulate different pieces of software anywhere along this process with pre and post processors to allow the data to flow seamlessly from one component to the other. And then above and below these puzzle pieces is tying it into supporting databases. These could be databases of ground motions. They could be tying off to other like USGS, OpenSHA, bringing in information from there. And then also coupling it with uncertainty quantification tools. Now, if we take that kind of those puzzle pieces, in the middle part of this diagram here, there's a number of software components that basically mirror what those puzzle pieces are, going from the hazard, the inventory, doing the analysis. And so we piece those together and then connect them in on the lower part of this slide with a lot of existing tools. And I should point out in NEARI, or the Sim Center, we're not, say, so much developing a new analysis module for anything. It's more just kind of streaming these things together in a consistent way. Although in some cases we are building unique software modules where there's nothing existing that fits the need. But then on top of this, these modules, we're combining them in different ways with different applications. And I'll talk briefly about the sort of kind of application software. But the key thing is we're being able to reuse these kind of modular software components in different ways. So everything that I just described is in the middle of this kind of green box here. And this is just showing that within this NEARI, the NSF supported infrastructure, the idea is that all of this software is running on high performance computing, in this case, using the Texas Advanced Computing Center, not just for the high performance computing aspect, but also for the data management. So the whole thing of this kind of workflow is to make it more convenient for users to tap into the different modules and to run projects, either computationally intensive ones on the high performance computing or on their own desktop. So the workflow applications that I mentioned that we build on top of this, so these are graphical user interfaces, kind of menu driven systems, where something called QuoFem, where we're coupling finite element models with methods to characterize uncertainties and to optimize, to look for, say, model parameters and so forth. So there's QuoFem. We then build that into different hazard modules. Today we're talking about earthquakes, but we're also looking at hurricane, wind effects, and storm surge. The next layer down, performance-based engineering, taking the responsive structures and looking at the damage and the economic impacts. And finally, taking these structure-specific applications and building them into a regional tool where we could take these very detailed models and apply them over large regions. So I'll talk about a few components of this workflow and also some sample applications or test beds where we're applying it. So the first is looking at how in this workflow we're characterizing the earthquake hazard. So one way is through more of a conventional probabilistic seismic hazard. Here we're tapping into the features to tap into the USGS OpenSHA through APIs and also the GEM, the OpenQuake. And through this, then you could either create scenarios or probabilistic descriptions. So if you look at scenarios, though, to come up with target spectra, and these could be uniform hazard spectra, conditional spectra, other metrics, such as the durations associated with a given scenario. And then coupling these with tools to select and scale ground motions to pull these in to, say, match those spectra if you want to analyze structures in, say, a time series. And another option in the workflow is, of course, to bring in earthquake records themselves. They could be coming from the simulations that we've been talking about in the last few days. They also could be just from recorded events, and I'll show an example of that. And also coupling this with site responses. So if you bring in simulated motions to actually, if you have the soil data, be able to propagate those through that geotechnical layer, such as John Stewart talked about yesterday. So I wanted to show kind of one application that we did of that. This was shortly after the earthquake in Anchorage a few years ago. So we spun up quickly one of these regional test beds with a few things in mind. One was to kind of demonstrate how these simulations can actually support reconnaissance efforts if we spin them up quickly after an event happens, and making very detailed estimates of damage, how that could help guide reconnaissance and how information from reconnaissance can start to help us validate and calibrate these models. But also I wanted to talk here about, through this process of creating a building inventory and the ground motions, we're going to look at two sets. In one case, we used the recorded ground motions that were actually recorded in that event. You can see the stations here, it's kind of sparse. We associated these with the different buildings in the area by kind of a nearest neighbor sort of approach. And then we calculated losses. We also calculated extensive damage, which we red tagged or collapses. But one of the things we could do in these workflows is to swap in different modules. And in this case here, we swapped in using kind of a scenario-based simulation of the ground motions using GMPEs and selecting ground motions as an alternative to the actual recorded ground motions to assess that effect. And so you see that those puzzle pieces shown on the right here. I wanted just to draw your attention to some of the resultant output, because I think one of the questions that's been raised, if we look at all the parameters, say on the ground motion, which of those parameters and characteristics are important for the output? And it depends on what you're trying to calculate. So in this case here, if you look at the table at the upper left, when we use the two ground motion sets, the sparse set of actual recorded motions or the more broad set of kind of the simulated, if you will, we got, in terms of total repair cost and loss ratios, very similar answers. But an interesting thing, if we looked at the extreme damage to structures, we got a large difference in the number of, say, red tag buildings. Well, these numbers are quite far apart. In this footnote down here, it shows that the kind of simulated ground motions actually came closer to what was observed. But there was a lot of houses that were damaged. So even that 3,800 number is not out of the ballpark. One thing this shows, though, is that where you might be able to calculate average loss is good with a sparse set of, say, ground motions. If you want to get the extremes, that is the extreme damage, you need a more kind of fuller representation characterizing uncertainties. Another part of the process I'm going to talk about is estimating response. This is kind of that QuoFem tool I talked about before that's coupling finite element model simulations of structures or geotechnical structures with different types of statistical and optimization algorithms. We could use these, for example, to optimize parameters if we have experimental data for models. We could also use them for sampling to propagate uncertainties forward. But I think one of the important uses will be to develop surrogate models. And so, for example, if you want a finite element model, you subject it to a lot of ground motions, maybe randomize the parameters in it. It's actually very similar to what Norm was just describing for the seismological models. You could imagine doing this for structural models too. So there's a lot of uncertainties there. You can't afford to run these all the time. So to develop a sort of surrogate model for these. So I'll show one example of some recent work on that. This is one where we're taking nonlinear models of structures, and we're trying to develop a surrogate model to capture the important features of ground motion. So we've heard in a number of talks, ground motions, you could think about a spectral acceleration intensity at the first period, but we also know, shown from this graphic on the left, that it's not just the first mode period, but it's the spectral shape. Some spectral shapes being more damaging than others, and there are metrics like SA average to kind of capture that effect. And there's also earthquake duration. So these are some of the ground motion features we want to calculate or capture in our structural analysis models. So there's different strategies for doing this. We've heard several talks that talk about the so-called multi-stripe analyses. That is one where you go to a certain earthquake intensity and say you can, from deaggregation of the hazard, you could develop a characteristic spectra based on the epsilons Jeff Bayless talked about, that characterizes the spectral shape, and you could bring along duration with that, and you could pull out a bunch of ground motions to match that hazard. But of course, as you get to higher intensities, that spectral shape changes, so you have to keep changing your ground motions. But for these surrogate models, another approach we're looking at is the site-specific adjustments to incremental dynamic analyses. So this is one where we would basically take a set of ground motions, where we would call them gridded ground motions. We pick a set of ground motions that have a range of SA ratios, that is spectral shape, have a range of duration. So we would take the set of ground motions, run an incremental dynamic analysis with them up to different intensities, and then we could look at different engineering demand parameters. So in this case, we could look at story drift ratios of 1% or 3%, or we could look at collapse metrics. But as you see on this plot on the right, by taking a log linear model or surface, we could then start to relate these collapse intensities as a function of the other auxiliary ground motion parameters, SA ratio, spectral shape, and duration. And what we could then do is statistically, we could, in this case in the lower left, we're looking at these fragility functions or cumulative distributions for exceeding certain drift ratios. We can actually adjust these for certain SA ratios and duration. And this would be taking this sort of one model of a building under one set of ground motions and being able to adapt it for different sites. So for example, if we went to Los Angeles and looked at the 24-75-year return period ground motion, here we're comparing this lower plot, a multi-stripe analysis, kind of a proven technique with this site-specific adjustment framework. And the advantage here is we could calibrate this model once and use it many times for different sites at different levels of intensity. Now, one of the things, limitation of this model is we calibrate kind of one surface, as shown in the upper right, for each engineering demand parameter. We could look at more robust tools, and this actually wasn't scripted, but I was surprised Norm showed this, talked about this PLOM, probabilistic learning on manifolds. We actually came across using the same algorithms here, these robust statistical algorithms, to process that data that I showed on the previous page, where we're not only capturing the mean values, but we're also capturing correlations between all of these parameters. So for example, if we want to know the peak drift at not just at any one floor, but at all the floors together, which is important for making, say, loss estimates, that this sort of model can capture that. And what's shown on the lower right is just how well it's doing in terms of just not capturing the mean values, but also the standard deviations and correlations between parameters. So there's a lot of promise, and part of our workflows is to find and incorporate these sort of tools that researchers can easily get access to and experiment with them. Another aspect of the problem is looking at the loss assessment. Here we've developed a library of different functions, starting with some folks that are familiar with HAZUS vulnerability functions, or for building detailed FEMA P58 that follow, say, the peer methodology. And you can imagine different paths through calculating damage. Some of the vulnerability functions go from an intensity measure right up to the damage or decision variable, kind of a very empirical model. The ones that follow the peer framework or FEMA P58, we take this bottom path where you take the intensity measure, get ground motions, go through time series, get responsive structure, and get damage. So we could accommodate these different methods in this library that users can call up. One application we ran on this on another peer project was, this was from the California Earthquake Authority, who was trying to demonstrate the economic benefits of retrofitting the cripple wall in houses. These pictures on the left showing examples from the Napa earthquake of a retrofitted and unretrofitted house. And here, what we need to have are models that can differentiate behavior at a very localized level. Shown on the right, for example, are the typical HAZUS vulnerability functions, which are calibrated to data. But as you can see, spectral acceleration versus damage, it's all over the map, but the HAZUS picks it up well on average, but it can't really differentiate the differences between houses, and in particular ones that are retrofit and non-retrofit and the level of retrofit. So in this project, we took the FEMA P58 type methodology, taking a number of kind of archetype houses of different, say, structural or different finishes, wood siding versus stucco, 1-story, 2-story, taking them through detailed nonlinear analyses with open Cs, different ground motions, and then estimating the economic performance. But the challenge here was we had about 250 pair or 125 pairs, 250 different buildings to do this on, that would entail about over 100,000 nonlinear dynamic analyses, coupled with millions of statistical kind of loss analyses. And so the workflow for that is shown here. What we're able to do is use the SimCenter workflow to kind of, again, make this process more seamless, that it allowed us to conduct these analyses over a week or two, what, you know, a few years ago would have been quite a laborious process. And the end result of that was coming up with demonstrating these different loss functions for buildings that had with and without the retrofit, demonstrating the non-retrofitted case on the left to the retrofitted one on the right, where, you know, folks that were skeptics say, well, you retrofit the cripple wall, it just throws the damage up into the upper part of the structure. Well, that's true, but it's decreasing the overall loss quite a bit. So I think where we're heading, this is another workflow we did. This actually used the Lawrence Livermore, the SW foreground motions. I think Art Rogers will talk more about those later. But this was kind of a proof of concept to scale up these workflows. We took the simulated ground motions, took 1.84 million buildings, built a simplified OpenSeas model, nonlinear analysis model for each, did 25 realizations of the building models, varying its parameter, calculating losses, and doing very detailed simulations over the Bay Area. This ran on the high performance computing, about 16 hours on about 13,000 cores to run all those nonlinear analysis. This was, again, given the ground motions coming into it. But part of what this testbed demonstrated was that, in fact, we ran similar ground motions to what was done for the Hayward scenario that uses kind of HAZUS methodology and uses census block inventories to think about what we can do with these sort of tools with very high resolution in terms of going down to the parcel or building level, these sort of analyses. And the point is, instead of just getting aggregated losses, how these sort of models can actually give us more detailed information on the vulnerability of specific types of buildings and in particular neighborhoods, and also maybe even socioeconomic demographics of the neighborhoods. So these very high resolution models open up new opportunities to really not just engineer buildings, but to help engineer policies, building code requirements, and so forth for cities in different regions. So
Dr.
one example.
Oh, sorry, you have 1 minute.
Okay, great. I think that's about right. So, you know, one example of what you could do with this, we looked at the issue at some of the existing tall steel moment frame buildings, these so-called pre-Northridge ones, where it's not just the damage to the building, but if they get damaged and they have to put a cordon around it, how that impedes the recovery of buildings around that. So this is just one example of what you could do with these kind of high resolution type models. Now, this raises, though, a number of additional questions coming back to the question of modeling uncertainties and correlations. We've talked a lot about the spatial correlations of geologic features and so forth and wave propagation to calculate ground motions. We also have that in inventories of buildings and the characteristics of those buildings and the variability in that. And also even when we go to recovery, there's a whole host of other issues there. And so my message here is just that we just keep sight of, we want to get each part of this process right. We focused a lot in the last day and a half on the ground motion, but see how things propagate through, and also appreciate that depending on what question we're trying to answer at the end of the day in terms of a policy that the city of San Francisco might invoke, to think about that everything needs to be accurate enough to give us a reliable answer. So just the last slide is just thinking of this extensible workflow that the Sim Center has been developing. The puzzle pieces are here, but the idea of this is you could keep adding on to it. If one's looking at kind of policy changes, they might want to look at urban planning models or policy interventions to change the inventory of cities, how they might change in the future, and then simulating what the effects of those. There's a lot of opportunity to continue to plug and play different sort of modules. And then as we go to the right side, a whole opportunity to connect more with social scientists on socioeconomic and recovery factors there. But I think we're at an interesting point in time where if we're careful about putting these puzzle pieces together and paying attention to saving the data, sharing the data and so forth, that we could really get a lot further kind of working as a community, kind of linking together these pieces. So I'd like to thank you for your attention this morning.